and sharing. Okay, is the lecture recorded now?
Yes, it is.
Okay, that's good. That's good. It always has some issue about the layers for the for this kind of presentation slides. Yeah, fortunately solved. So let me repeat this one again. So basically, for the direct demand model, we're gonna have some. Usually, we're gonna apply some linear or some linear format of the equations to show the relationship between the some demand variables and supply variables with respect to the trips that you're going to estimate. And one of the classical model is the Washington-Boston corridor study. And this one will explore the demand or the number of the trips traveling between Washington and Boston. And this one is between Washington, D.C. and Boston. And the study was conducted in 1963. It's a quite an old study, but it gives us some classical model about the travel demand models. So basically, the model assumed that the number of the trips from the origin I to the destination J with the mode M. So it could be the auto, could be the train and something else with the purpose of with the specific purpose. And in this case, that will be the personal trip or the business trip. And the trip will be in the function of the population, the income level, the travel cost by the specific mode and travel time of the specific mode. And also here you need to know what's the population and income for the two cities, Washington, D.C. and Boston. And in the equation, you can see that there will be a lot of parameters. The value of A, the variables parameters of A, B, and C should all be the coefficients we need to calibrate. And also there will be some product sign which will show the to represent the relationship between the about the cost of all different modes. And if we refer to the original definition about direct demand models, we have the demand variables, we have the supply variables, and in this direct demand model, the part with respect to the population and income will be defined as the parameters for the demand, and for the supply part, it will be related to the cost of the trip and the travel time of the trip with a specific mode. And this is the traffic. This is the one typical direct demand model. And regarding to the calibration of this model, it's kind of the linear format, but it's not a direct linear equation. So what you want to do is for the calibration, you need to apply the log transformation on both sides. And once you have applied log transformation, you will be able to extract them to the linear formation. They will be in the function of the and eventually there will be in the log t will be in the function of a set of the observed variables, which could be shown here, including the population, the income levels, the cost of the trip, and the travel time of the trip. And there are also some unknown parameters, and these would be the parameters you need to calibrate from the observed data with the linear regression. And once you have all these parameters calibrated, you will be able to use the model to estimate the number of the trips traveling between Washington and Boston, as well as the make some predictions about the future trips. So that's one typical direct demand model. And The next example is the DKV model. It's proposed in 1968. You can see that there will all be some old models. This one will apply the linear log form to determine the work-related trip by passenger cars in the urban area. So this is it will have the equation to just designed for the work trip and the passenger cars. And this is the expression of the model, and it shows the number of the trips traveling from I to J, from the origin I to destination J with the mode M, which would be the auto, and with the purpose of work. And in this equation, you can find out, you can also link it back to the demand and the supply inputs. For the demand, that will be the part related to capital S. And here in the model, S will represent the labor force at the origin, the employment at destination, the income levels, and the ownership of the auto or the vehicles per each person at the origin. And you also can see the portion with respect to the supply, and that will be the variable of L, which will be the related to the travel time in the vehicle, and also the travel time outside the vehicle, which means the working time, and you also related to the cost you need to spend for the trip, like with the parking fare, or if you need to go through some toll roads, what's the rate of the toll, and so on. So that's the that would be the another one, the DKV model, and it's only designed for the work trip with the passenger cars. It also has another component for the other type of the trips, the shopping trips with the passenger cars, and the work trip by the transit. So this one can represent two different type of the trips. And the equation is still very complicated. In the model, you can see that the again this portion, the yellow part shows the input related to demand, and this part shows the input with respect to the supply. And also, this model can be easily extracted. If you do the log transformation, it can be easily transferred into some linear format. I will just skip the process, the detailed process about the transformation. So you can go to check how you're gonna convert them to the linear equation about this model, and you just need to calibrate the parameters A, B, and C to use this model for the estimation, for the trip estimation and prediction. And the third one is the quant and Bormer abstract mode model. This one is also proposed in 1960s. The model is even more complicated. It shows the number of the trips traveling from the origin I to destination J with the mode M. And here it has an additional parameter, which is F, which represents the frequency of the service. What's the frequency of the transit or the frequency of the trips will be. And B here represents what's the best parameters we can use. Well, with this model, you can also identify the parts with respect to the demand input that will be related to the population and income. And the other part will be related to the supply, including the cost of the trip, the travel time of the trip, and the frequency of the service, and so on. Again, like you can also convert this complicated model into the linear format by applying the log transformation. And with this log transformation, you will have the observed quantities of the demand and the supply variables, as well as you will find some unknown coefficient, the alpha A0, A1, A2, tier A10, and those would be the parameters you need to calibrate from the for the direct model. So you can see that for all these three models, even though it's straightforward, it's quite easy for you to find out what's the number of the trips traveling from one origin to one destination with one specific mode, specific purpose, directly based on the observed data. But the equation will be very complicated, and you have a lot of variables to collect, either through the survey or based on some automatic data trip collection method. But this kind of data collection would be very costly. In the meanwhile, the calibration will take a lot of effort, and you know that for this kind of linear regression model, it will also be very difficult for you to extend to the other areas. Like if you have this kind of model, for example, for this model, the abstract mode model, if it applied at CDA, it will not be easy for you to extend this one at a CDB. You probably need to filter out some parameters and recalibrate the model with the to find out a large number of the coefficients, and then you will be able to use the model in the other CD. So there will be a lot of work, and due to this kind of less flexibility of the direct demand models, nowadays we actually change the most of the cities, the metropolitan areas, they change their planning model to four-step models instead of applying the direct demand model. So that's also the major topic we're going to cover in this class. So for the four-step model, we will go through the trip generation, trip distribution, mode choice, and route assignment. And this would be the four typical steps. We will start with the trip generation in this class. So first of all, the trip generation, it will help us to determine how many of the trips will be generated from one location. And we don't care about how many what's the destination it is, but we have to know how many trips will be generated in that area, or how many of the trips will be attracted to one location. So that's the purpose of the trip generation model. Before we go to the details about how to conduct the trip generation models, we need to have some specific definitions. The first definition, which is the most critical one, is what is trip? How are we going to define the trip? Generally the trip is defined as the one-way movement of the person or the goods from one point of the origin to the point of the destination, just the movement from one location to another one. So this is defined as one trip. And if now we have the definition of the trip, then we need to define the different type of the trips that we can model. So usually in the transport planning, we will classify the trips as the home-based trip and not home-based trip. So for the home-based trip, which is HB, is defined as the trip where either the origin or the destination is the home location. So if one end of the trip is origin, it's the home, then we define this one as the home-based trip. And the home is not necessary to be the origin or the destination. Either way is fine. So let's go to see one example. For example, if we consider the trip from the home to the work and then return, so there will be two trips. Trip 1 is from the home to the work, and trip 2 is from the work to the home. And then in that sense, we will have two home-based trips. Both of them, trip 1 and trip 2, will be defined as the home-based trip because the home is placed as the one end of both trips. And the other type of the trip, which is a non-home-based trip, is defined as a trip where neither the origin nor the destination is the home-based trip. Basically, the other type of the trip, the type of the trips other than the home-based trip, they're all defined as non-home-based trip. So in this case, we can define, we can see another example, the trip from the work to the shop and then return. So for example, the trip 1 is the start from the work and to the shop, and trip 2 start from the shop back to the work. And in this case, we're gonna have two non-home-based trip. And also, this is just one type of the definition about the trips. We also need to know that how this kind of home-based trip and non-home-based trip will be differentiated from the origin destination and the purpose and the production and attraction. So first, let's go to see the definition of the origin and destination. So the definition about origin destination will be straightforward. The start point of the trip is origin. The end point of the trip is destination. So for the first example, trip 1 origin is home and destination is work, and trip 2 origin is work and destination is home. And similarly, you can find out the origin destination for the second example between the work and the shop. So that's the first definition. And the next thing we want to define is the production and attraction. So regarding to the production, it's defined as the home end of the home-based trip or the origin of the non-home-based trip. They will be defined as the production. And this is a little bit different. It's a little bit confusing compared with the origin destination. So let me go to check the example in the previous page to see how we're going to define the production, how we're going to specify the attraction. So for the example, let's take the trip from the home to the work and then return. So we have two trips. The production is defined as the home end of the home-based trip. So we know that in this example, both trip 1 and trip 2 are the home-based trip. So the production will both enter the home end. So we have the production for at the home for trip 1. We have production at home for trip 2. And for the other example, the trip between the home, between the work and the shop is different. This would be for the trip 1, trip 2 in the second example. Both of them are the non-home-based trip. In that sense, the origin of the non-home-based trip are defined as the production. So for trip 1, the work site will be the production, and for trip 2, the shop site will be the production. So this is the definition for the production. And with that, we can easily define the attraction. The attraction is defined as the non-home end of the home-based trip or the destination of the non-home-based trip. So back to the first example here, for the attraction, that will be the non-home end of the trip. In trip 1, which would be the work site, and in trip 2 is also the work site. So we have two attractions at the work. And for the second example, it's different. The destination of the non-home-based trip will be the attraction. So for the trip 1, the attraction is the shop, and for trip 2, the attraction is work. So that's the how we're going to differentiate the production and attraction based on the purpose or the type of the trips. And with that, we can then make some more summary comparison about origin, destination, the type of the trips, and the production and attraction. So here you can see that for the home-based trip, the origin and destination is not necessarily the same to the production and attraction, but for the non-home-based trip, the origin is just production, and destination is just the attraction. Another thing we want to further cover is the some notations. The first thing is the zone, which would usually be referred as the TAZ zone, the traffic analysis zone, and it will give us the region where we want to estimate the number of the trips, total number of trips in that area, and we also need to have some clear ideas about what's the difference between the origin destination and the production and attraction. They are not the same. And the third one is the trip table, which will tell us how many of the trips will be generated for each city, and based on different categories of the income, could be the income categories, the car owner categories, and the educational categories, and so on. We will show more details about that later. But first, let's go to see a more complicated example, and then try to identify the difference between the origin, destination, and production and attraction. So here, let's consider the 3 points. Includes the home, work, and shop. And we have the trip from the home to the work, and from the work to the shop, and then from shop back to the work, and from the work back to the home. Just considering this is some pre-pandemic routine for the regular person. They will do the commute to their workplace, and then at lunchtime, he will go outside and take a lunch, and then back to work. And at the end of the day, will drive back to the home. So this is kind of the regular trips that each one person will take for their daily trip, for their daily activity. And we will specify 3 regions. Region 1, the home is in the zone 1, work in zone 2, and the shop in zone 3. And with the 3 zones, we can then specify what's the how many origins in each zone, how many destinations, and how many production and attractions, and how many home-based trip and not home-based trip. So let's list this a table. So for now, we have 3 TAZ zones, and in the let's start with the origin. In the zone 1, we have 2 trips, trip 1 and trip 4. And in that, for trip 1, the origin is in zone 1, and for trip 4, zone 1 is their destination. So with that, we can say that zone 1 will have one origin and 1 destination. Similarly, you can apply this kind of same definitions to the other zones. For zone 2, there will be 4 trips, and trip 1, zone 2 will be the destination of trip 1, and trip 3, it will be the origin of trip 2 and trip 4. So you're going to have 2 origins and 2 destinations. And for zone 3, similarly, you will have 1 origin and 1 destination. So that's the origin and destination. So with that, we can find out Zone 1, there's 1 origin, 1 destination. Zone 2, 2 origin, 2 destination. Zone 3, 1 origin, 1 destination. Totally, we have 4 origins and 4 destinations. This makes sense because we have 4 trips. We will have 4 origins and 4 destinations. And the next thing which I would like to leave for the class, do you know how many home-based trips and non-home-based trips in each zone? Let's start with the zone 1. So how many home-based trips and non-home-based trips? Anyone has an idea about it? So can anyone give me the number about these 2 values?
Two.
So two what values? What type of trips? Yes. So 2 would be the right number. We have so for both trip 1 and trip 4, they will be the home-based trip because the one end of the trip will be the home. So they are both would be the home-based trip. And we don't have any non-home-based trip, so that will be 0. What about the zone 2? So we have 2 and 0. What about zone 2? How many home-based trip? How many non-home-based trip?
2 home-based trips and 2 non-home-based trips.
Okay, so which 2 will be the home-based trip? Which 2 will be non-home-based trip?
Trip 1 and trip 4 is home-based trip, and trip 2 and trip 3 is non-home trip.
That's great. That's right. Yeah. So trip 1, trip 4, it has home end, so they are always the home-based trip. And trip 2 and trip 3, now they will have the home end, so they will be non-home-based trip. And then for the zone 3, what's the idea you're gonna have?
0 home-based trips.
So we have 0 home-based trip and
2 non-home-based.
2 non-home-based trip. And if we sum them together, there will be 4 home-based trip and 4 non-home-based trip. And the next thing we're gonna ask is what's the number of the production and attraction for each zone? I'll start with the TAZ1. How many productions in the zone 1, and how many attractions there?
1 and 1.
Can you really think about it? So the I'm give you the definitions about the production. The production is the home end of the home-based trip, or the origin of the non-home-based trip. The attraction is the non-home end of the home-based trip, and the destination of the non-home-based trip. So with this definition, what's the can you let us know what's the how many productions and how many attractions in zone 1? Any idea about it? I probably can give you the number first for the zone 1. So the production is the home end of the home-based trip. So trip 1 is a home-based trip, and trip 4 is also the home-based trip. And for zone 1, home is the home end, definitely the home end. So home end is always the home end. In zone 1 it's always the home end. So we have production. We have production for trip 1 and production for trip 4. So which means that we're gonna have 2 productions and 0 attraction. That's for the zone 1. What about the zone 2? Any idea about the value in regarding to the production and traction? Any ideas about the value? It might be tricky. So still, let's go to see the trip 1, trip 4. So zone 2 is the null home end of the this 2 home-based trip. So this is the attraction. For trip 1 is attraction. For trip 4 it's also attraction. And for the trip 2 and trip 3, both of them are the non-home-based trip. But for the non-home-based trip, the origin is the production. So it would be the production. Zone 2 will be the production for the trip 2. And zone 2 is also the origin of the trip 3. Trip 3 is a non-home-based trip, so it's an attraction. So with that, we have 3 attraction in zone 2 and 1 production in zone 1, in zone 2. So it's a 1 and 3. And similarly for the zone 3, they are the non-home-based trip. So we have 1 attraction, 1 production. So that have 4 production, 4 attraction. So that's what we calculate for the origin, destination, home-based trip, non-home-based trip, and production attraction. And if we make a comparison, you can see that the total number of the origin and total number of the destination, they will be same. This is actually always true, because for any trip, it must have an origin and one origin and one destination. So if we sum them together, the number must be the same. And for the production and attraction, if we do their summation, they will also be the same. This is also always true, because usually for one trip, if the one end is a production, the other end must be the attraction. So if we sum all of them together, it will always be equal to each other. But for the home-based trip and non-home-based trip, even though in this example the number are the same, they have 4 different trips. But the issue, in reality, they are not the same. Usually they are not the same. Which means that the number of the activities related to the home with respect to the number of activities not related to the home are not the same. For example, if there's one person who just taken a trip to the work, and he take his own lunch and eat at work, then it's not necessary for him to go to the shop area. So with that, you will probably have you have 4 home-based trip at zone 1. You have 4 home-based trip in zone 2, and 2 non-home-based trip in zone 2, and 2 non-home-based trip in zone 3. And if we summarize them together, you get 8 home-based trip and 4 non-home-based trip. So they are not equal to each other. So the example is just a specific case to get the same value, but in general, they are not the same. So that's the relationship between the origin, destination, home-based trip, non-home-based trip, production, and attraction. Just try to remember their definition and know their differences. This one is quite useful it's very important for us to determine the trip table to identify the number of trips traveling from one origin to one destination. The next concept we're going to introduce in the for the trip generation model is the trip table. So the trip table will shows how many of the trips for traveling from one location to another one and return back to the home. So in this case, we have 3 zones. So we have zone 1, 2, and 3. And the trip table will identify how many of the trips from departed from one zone to another zone, which indicates that for this specific case, we have 3 by 3 matrix to determine the number of the trips for each origin and each destination. For this specific example, if we go to check the defined trip from zone 1 to zone 1, there isn't any internal trip, so the number is 0. And for the zone 1 to zone 2, there's 1 trip, which is trip 1, so we have 1 number. From zone 1 to zone 3, no direct trip, so the value is 0. And similarly, you can find out the trip from zone 2 to the other 2 zones. From 2 to 1, there's 1 trip, that is trip 4. From internally, no trip. And from 2 to 3, there's 1 trip. That is trip 2. And similarly, you can find out the trip from zone 3 to the other 2 zones. No trip from 3 to 1, but there's 1 trip from 3 to 2. That is trip 3, and no trip from inside the zone 3. So with that, you can then find out the define this kind of 3 by 3 trip. This is what we want. And if we go back to check the table that we calculated previously, you can find that to do the summation, the total number of the trips from the if you do the summation for each origin, then the total number of the trips will be the same to the origin, that is 1, 2, and 1. And if we do the summation for each destination, you can find that this value is the same to the destination that we calculated, that is also 1 to 1 in this example, and the total number of trips would be 4. So basically, if we just counting the number of the origin destination, you can determine the total number of the trips from the origin or to the destination. But the trip table will give you more details about how many of the trips from one origin to one destination. So that's the definition of the trip table. And the next thing we want to consider is the how we gonna we have some definitions about the trips, but the other things like how we gonna classify those trips. We classify them based on the purpose of the trip, based on the time of the trip, and so on. This kind of classification is applied for us to determine different trip tables with respect to different purpose and different time of the day. Usually, the trip purpose is one of the important factor for us to classify the trips, and it's especially for the travel demand models. It's very important for us to separate the trips with different purpose. For example, for the trip to the work and the trip to the entertainment, they have very different features. If you mix them together, your model will not be accurate because they cannot reflect the usually for the trip to the work, there will be the mandatory trip. No matter what kind of cost you need to spend, you have to go there. But for the trip to the entertainment, it's very sensitive to the cost of the trip. So if we put them together, your model will be less accurate to describe the actual behaviors that people will take in the network. So for the home-based trip, usually we can categorize them. We can define them in 5 different categories. That could be the trip to the work or the educational trip. These 2 will be the mandatory trip. The educational trip will or indicates the trip that you have to drive your kids to their school, or if for the college students, they may need to drive to the college to take the class, something like that. And for the other three types of the trips, the shopping trips, the social and the recreational trips, or the other type of the non-routine trips, they are optional. So we call them as the discretional trip. If we make a comparison about the relationship between the cost and the volume, you can see that for the mentor trip, it's not sensitive. The volume is not sensitive to the cost. But if we go to check the discretional trips, the shop-related trip and entertainment-related trip, it will be very sensitive to the cost, and especially for the entertainment, at a certain value, a very small change of the cost will cause significant changes about the volume. And for the non-home-based trip, usually we want to separate them, because generally this kind of non-home-based trip will only represent 15 to 20% of all the trips. So we will usually consider them as one category. So that's the classification based on the home-based trip, based on the trip purpose. And the next one is the classification based on the time of the day. So we will usually discretize them with the into the peak hour and off-peak hour. And the percentage of the trips for different purposes will also vary by the time of the day. Like for the peak hours, there might be a huge percentage of the mentor trips. At off-peak hours, the percentage of the discretionary trips or the non-home-based trips will take a very high percentage. So we will need to combine these two together, like categorize the trips based on the purpose and also time of the day, for us to get an accurate model of the trip table. And regarding to the factors we have to consider for the calculation of the production and attraction, they have usually for the personal trips, for the personal trip production, it will be determined by the conditions of the individuals, the financial conditions, the income level, the car ownership, how many cars were owned for each person, the household structures, like the marriage status, the whether there's any children at the home, or the stages in the life cycle, and so on, and the value of the land, the residential densities, and also the accessibilities of the region. So that's the some critical factors for us to determine the production. And for the attraction, is more related to the entertainment and the employment conditions, including the space, especially the parking space. Also the population density has some impact to the attraction, and the employment opportunities that could be including the retail and the commercial, the industrial, or other service providers in that area. So you can clearly see the difference. The different parameters will be applied for us to determine the production and attraction. And for the trip generation step, we will focus on estimating the trip production, and also this model can be extended for the trip attraction. To estimate the trip production, we will assume that the production will be in the function of all these important factors. So we can just simply write the number of the trips will be some functions of the income, car ownership, household structures, and so on. And we need to find out a model to determine which parameters would be the most important variables for us to determine the trips, or the productions. If we are using the some closed form function, like say that the production is the function, a linear function of the income, car ownership, household structures, or some linear format of the functions, then we can apply the regression model to determine this relationship. Or if we don't have any specific closed form expression about this relationship, then we can go to see two simple models. One is the cross classification or the category analysis method. The other one is the multi-classification analysis, MCA. Well, for the lecture today, we will start with the simple one, the CCA and MCA. So let's first go to check the CCA method, cross classification analysis. So for the idea about the cross classification analysis is like we will assume that the trip generation rate is stable over time for some household stratification, which means that the household structures and distribution. So with that, in this method, we will divide those households in the area in one TAZ zone into multiple categories based on their income levels, the car ownerships, or the family structures, and so on. And we assume that we have a set of the categories, and each category is defined as one cell, and the household within each cell are assumed to be homogeneous, and they will be different. Their behaviors or their decisions about taking the trips will be different from the other cells. So that's the assumption we made for the cross classification analysis. And so with that, we can have the a set of the table like this one, and this one will tell us how many household in each category, and this kind of category are defined based on the household size and the number of the cars owned by each household. So we consider the household size with 1 person, 2 to 3 person, 4 person, 5 person, and more. And for the number of the cars, we consider 0 car, 1 car, and 2 more cars. And this, based on the survey, we can find out, for example, for the household with 1 person and no car, the number would be 28. 1 person with 1 car would be 21. So there are 21 households with only 1 car and 1 person. And you can also find out the values of the other category. So with that, we assume that the number of the trips in each cell will be homogeneous, and the person in the same category will have the same number of trips they're going to take. So which means that their distribution will be very concentrated. You can just use the value, the mean value, to determine or as an estimation about number of trips they're going to take in each cell, especially in one specific cell. So with that, we will define the value. We will define the number of the trip in the cell H as TPH, and we need to calculate what's the value of the TPH based on the cross classification analysis. So now let's go to see how to do this calculation. In order to do that, we first do some survey to check the number of the trip number of the observed trip with the purpose of P for the household type H. So the number of the trip in the survey for the category H to take. And this assuming that this table will tell us how many trips we're going to take in the in each cell. For the household with the say that for the household with 4 person and 1 car, they're gonna have a total number of the trip as 157 from the survey. And we also know how many household in each category for the specific category with 4 person in the household and 1 car. There are 90 households. And then if you have these 2 tables, the total number of the trip table and the household table, the the trip rate could be quite straightforward to calculate. Basically, the TPH would be the ratio of the total number of the trip and the number of the household in each cell. So for this specific example, for this specific cell, we have the TP as 157 and the household number as 90. So we get the value as 1.74, which would be this value. And similarly, you can find out the other values. For example, for this category, household size of 223, 0 cars with the trip number of the trips as 90, the number of the household as 150, so you get a value as 0.6. You apply this equation for all the cells, then you can find out the trip rate for the all the cells. And that will be done for the cross classification analysis. It's quite straightforward. And another thing I would like to introduce about, once you have the cross classification analysis result, how we're going to use that one for the transportation planning or for the travel demand model. So this one will require us to do some aggregation to the zone level. So that is the this kind of aggregation will do some summations about the trip rates over all the zones. So the total number of the trips from the origin I will be the summation of the number of the households in the cell I times the trip rate. So if we have basically if we have the let me just try to. So if we have 3 zones, zone 1, zone 2, and zone 3, for each zone you will have the trip rate. You have the trip rate table. We see that the trip table. And for zone 1, you will have the table for the number of the household in each cell. So that is A1H. And if you do AIH times the TPH, you will be able to find out the what's the total number of the trips in each zone. And so that's the way for you to find out the number of the trips, aggregate number of trips in each zone. And another thing is like probably in the future we want to make a prediction about how many of the trips can be generated in each zone, like in the next 5 years, in the next 10 years. But we don't know how the trip table is going to change. We just can assume that how the population is changing over the time. Then the calculation about the or the prediction should be conducted based on the assumption, which would be like the probability distribution of the household will remain the same as the same to the base year. So with that, we can then just increase the or find out the number of the household in the future year based on the changes or the increase of the total population over the years. Say that say that we have the population of the we have the household in base year as this one, and we can draw the distribution like for the household with the 1 person and 0 car, the percentage might be 28 divided by 988. 988 is total number of the household, which would be approximately 2.8%. And then we assume that this 2.8% will remain the same in the future. So it's 2.8 in 2020, and this type of the household will still be occupied 2.8% in 2030 or even longer period. So that's the assumption for us to utilize the CCA methods for the prediction. And the distribution will remain the same. And then if we say that the population, well, the total population of the zone I increased to HI in the future year in 2030, then we can still use this kind of distribution to calculate what's the number of the household in 2030. For example, this year 2020, the population is 2020 it's 988, and 2030 it increased to 2000. And for the cell 1, I get the percentage is 2.8, and for in 2030 it's still 2.8. Then the number of the household in the cell 1 would be 2000 times 2.8%. That would be 56 households. So AI1 for cell 1, that will be 58 in the future year. And then you can use AI1. We have previously calculated the number of the trips, and the trip rate in the cell 1 as TP1 as 0.11. So you can find out the number of trips in the the number of trips in the cell 1 as 56 times 0.01 or 0.11. That is approximately 0.6. It's approximately 6 in the future years. So that's how we're gonna use this model for the prediction. And the model is very simple, and it's very straightforward to conduct the prediction of the future trips. But they are also this is another equation I forgot to put it here. So you can use this one to make a prediction about the total number of the trips will be generated by each zone, and with a specific purpose. I say that for the cross classification method, it has some advantages. First, the model is very simple, and it's easy for you to calculate. The groups are usually independent to each other in different zones, and it can allow very general relationship between the number of the trips and the household characteristics. So you don't need to assume a linear relationship to do any regression. But there are a lot of disadvantages. First of all, it's impossible to further expand the model to some cells that has not been defined. For example, in the previous example, we assume that for the household with 4 or 5, say that with a 5%, say we only assume that there's a household with 5%, but it's possible that in the future there will be some household with more than 5%, 6 or 7% in the household. In that sense, for that condo, category, it cannot be modeled in the future. So this is apparently some limitations we have to think about. And the other things like there isn't any statistical goodness of the fit for this model. We cannot verify whether this model is statistically important and whether we can, if we apply this model to the other zones, whether it's reasonable, whether it's accurate. So it's hard to make any judgment about the goodness of the fit. Moreover, usually for this model, we need a very huge samples to make sure that we can achieve to certain accuracy. And generally for each cell, we need to have like more than 50 observations. So the cost of this kind of survey would be very high. And the next disadvantage is like the selections of the categories. This one is very important. In the example, we choose the number of the cars, the household size, but there are also some other parameters. Maybe the income level plays more significant roles in the model, but you missed to select that one. So if you use this one, you don't know, if you just choose this CCA method, you don't know whether you are choosing the right parameters to generate the trip table. And the other things like for the complexity of this model, actually if the number of the cells increase with the number of the categories, the number of cells will increase dramatically with the number of the cells. For the previous example, we have 3 categories of the number of the cars and 4 categories of the household size. So the total number of the cell would be 3 by 4, that is 12. But if you just slightly increase the number of the categories in each characteristics, for example, if we want to consider income levels, car ownership, and household owned structures, then it will increase dramatically. So like with 3 income levels, 3 car ownership or 6 income levels, 3 car ownership or levels, and 6 different household structures, then you will need to define 108 cells. And considering you need to have at least 50 samples for each cell, then you must have you need to make a survey for more than 5,000 households, and that will be a very huge task for you to complete. And you need to spend a lot of money to complete the survey. So it's just not quite efficient to do that. And regarding to the prediction models, and they have some assumptions like the distribution will not be changed over the year, but in reality, this kind of distribution might be changed over the years. So regarding to the prediction model, it will not be accurate. And also, if you go to check this model, it only considers the parameters related to the demand, does not consider anything about the supply, the cost of the trip, and so on. So the model that it creates will definitely not sensitive to the supply, and it will not be a good model if we cannot reflect the impact of the cost of the trip. So that's that would be the disadvantages of the CCA model. actually most of these advantages and disadvantages also applies to the next one, the multi-classification analysis method, the MCA method. These two are quite similar. Both of them are very simple, but they have a lot of disadvantages. So for the MCA analysis, the method is quite similar to the one we defined. If we consider the model with a continuous dependent variable, the trip rate, and if we also will consider two independent variables, like two different categories, two different characteristics. So it cannot consider more than two different characteristics. This is another disadvantage of the MCA method. So in this model, the household size is well, in the example for the rest of the lecture, we will only consider two variables: the household size and the number of the cars. And for the implementation of the MCA method, we will first need to find out the grand mean over the whole sample, and then we need to find out the group mean for each row and each column, which will be represent the mean for the origin and destination. And then we need to calculate deviation from the grand mean. And with that, we can then estimate the trip rate for each cell based on the summation of the deviation and the grand mean. I'm going to show, and if we find out negative value, we should set as 0. So I'm going to show you more details about the calculation. So first of all, assuming that we have a survey about the trip table, the total number of the trips in each cell, and the number of the households for each cell. And here we can only consider two characteristics of the household structure: the size of the household and number of the cars. And to implement the MCA analysis, first of all, we need to calculate the mean value. The first one is the find out the group mean. The group mean is the ratio between the total trip and the total number of the households. So for example, for the household with the household size with 1 person, the mean trip rate would be 23 divided by 4923, the total number of the trips for this category, and 49 is the total number of the household. So that will give you the value as 0.47. And you can find out the other values for the household size 223, that is 1.28. And that is the ratio between the total number of the trips, 568, and total number of the household, 444. And similarly, you can get the value of the other group means. And you can also try to calculate the group mean for the classification with respect to the number of the cars. For example, for the category without any car, the total number of the trip is 201, and the total number of the household is 276. So the mean trip rate would be 201 divided by 276, that is 0.73. And you can also find out the value for the category with one car with more than 2 cars. Another thing that you need to think about is the grand mean. The grand mean will represent the total number of the trips for all the categories with respect to the total number of the households. In this example, the total number of the trips that we consider is 1,525. And the total number of the household is 988. So with that, the grand mean is 1.56 or 1.54. So this is the grand mean we're going to use for the calculation of the grand deviation. And that's the first step. We find out the mean values, the mean trip rate with respect to different categories of the household size and the number of the cars, and the grand mean for the total number of trips and total number of the households. And the next thing we need to think about is the grand deviation, the deviation from the grand mean. And that one is straightforward. Basically, you just need to find out the difference between the mean value and the grand mean. For example, for the household with one person, the deviation of the grand mean would be 0.40. That would be 0.47 minus 1.54. So that is minus 1.007. And similarly, you can find out the value of the second category. That is 1.28 minus 1.54. And you can find out the other two values for the size of 4 and 5. And similarly, you can find out the deviation with respect to the number of the cars. Minus 0.81 would be the grand mean. 0.73 minus 1.54, and this one would be 1.53 minus 1.54, and similarly you can get a value for the last one. So that's the deviation from the grand mean. And once you have these two values, two set of values from the household size and from the number of the cars, you can use this two vector and the grand mean to calculate the trip rate for each cell. So the calculation is also quite straightforward. So basically, for the trip rate table, for the cell one, it will indicate the value of the summation of the group mean, the deviation from the grand mean for the household size 1, plus the summation of the grand mean deviation from the grand mean for the category without any car, plus the grand mean. So that is 1.54 minus 0.81 minus 1.07. And you find out the value is minus 0.34, which if it's smaller than 0, then you must set this one as the 0. So this is one of the very important note. The trip rate cannot be negative. If you find out the calculation is negative in the trip rate, set them to be 0. This is just some manual change about the value. And you can also apply the similar process for the other values, like for the second one, for the second cell, that is 1.54 minus 0.01 minus 1.07, which will give you as 0.46. And similarly, you can get the value for all the other cells, and that's the trip table you're gonna get for the from the MCA analysis. And with that, you can make a comparison about the CCA method and MCA method. Basically, you can see clearly can see the difference for the from the CCA method. For this first cell, you get the rate as 0.11, but for the MCA method, you get the value as 0. But for the MCA method, you get this one as 1.37, but from CCA it's 0. So there are some difference, but they will all be some estimation from the observed data. It's hard to justify which one is better, which one is worse. Both of them would be in the simplification to find out the number of the trips from under different cells. But they have a lot of disadvantages. So we were usually not using this kind of method for the trip generation. Instead, we prefer to use some we prefer to apply some regression model to conduct the trip generation. And that's what we're gonna do. What we're gonna cover in the materials for the next lecture after the reading week. And here's another comparison about the calculation. So once we have the trip rate from the two methods, you can then directly multiply the household number to check what's the value you can calculate for the what's the number of the trip, total number of trip we're going to calculate for each cell, and that will be the one you're going to use for the future. With that, I guess that will be all for the lecture today, and we have approximately 15 minutes. So I would like to assign the quiz, a simple quiz for you to work to get some practice about the CCA and MCA methods. I'm going to upload the quiz to Avenue to Learn so that you can work with that. So let me try to upload a quiz on Avenue to Learn, and I'll just try to make it available for you to view. Okay, it's just uploaded, so you can work on that. So basically, it's just about the just giving some practice for you to know how to use the CCA method and MCA method. Again, once you finish that, you can actually upload the quiz on. Just upload them to Avenue to Learn. I will create in a folder there. I will make the folder available until 6 p.m. So you're gonna have sufficient time to work on that. Okay, I'm gonna stop here, and if you have any, do you have any questions before you start the quiz? It's some simple quick calculation, so you can use Excel to quickly get the result. Okay, if there's no questions, I'm gonna stop recording this one, and or you can work on the quiz.